Good morning, everyone. It's my great pleasure to introduce our speaker this morning, Charles Campbell. However, in the USA, we refer to him as Charlie, and I will continue to do so. So Charlie received his bachelor's degree in chemical engineering and then his PhD in chemistry from the University of Texas at Austin. He then did a postdoc period for a couple of years in Germany with Gerhard Ertl. After that, he came back to the USA, began his career with 5 years as a staff scientist at the Los Alamos National Laboratory, and then began the academic part of his career by going to the University of Indiana in chemistry. And at that time, he met the woman who became his wife, a musicologist, and they then found that opportunities were even better on the West Coast in Washington, the state of Washington, and so they moved there in 1989, he taking up a position in chemistry, she in musicology. So today, Charlie has the position of the Rabinovich Endowed Chair in Chemistry. He's also an adjunct professor in chemical engineering and physics. Since coming to Washington, Charlie has developed a very deep and multi-dimensional career and set of experimental studies, and now increasingly theoretical ones in different areas. I just want to mention a few of them. They include the reduction of both CO and NO, and in that area he was one of the lead people in developing a perspective on how CO is converted to methanol. He's worked on the electronic effects of metal support interactions, the kinetics of elementary reactions. He's developed ultra-sensitive techniques for measuring using calorimetry on a very, very fine scale, the heats of absorption and heats of reaction of elementary steps involved with transition metals and metal oxides. And he has developed a very widely used approach for determining what is the rate determining step in a series of elementary reactions. His work has been published in over 300 papers with 18,000 citations. This work has garnered him a number of awards, including the IACS Arthur Adamson Award, the IACS Award for Colloid and Surface Chemistry, the Welsh Award from the American Vacuum Society. He's also been a Gerhard Ertl lecturer. He's given the Robert Burwell Lectures of the North American Catalysis Society, and he has also been the Vladimir Ipatiev lecturer at Northwestern University. So without further ado, I'm going to invite Charlie to come to the stage, to the right-hand side over here, and present his talk on the thermodynamics and kinetics of elementary steps on late transition metal catalysts and using them to search for better catalysts. So Charlie, you're welcome.
Thank you. So it's a great pleasure to be here. My thanks to the organizers of the conference, and I really wanted to congratulate you on the wonderful programming that I've heard so far, and looking forward to the rest of the week. So the subject of the talk is mostly focusing on elementary step kinetics and using those to predict rates of reactions and search for better catalysts. I'm going to talk towards the end of the talk about the kinetics of things that happen with the metal atoms in the catalysts themselves and the energetics of those steps as well. One of the things that has guided me in my career is the work from Gerhard Ertl, and this is a view graph from his Nobel Prize lecture where he shows the energetics of the elementary steps in CO oxidation catalysis. And these pictures that he evolved for this reaction, for the ammonia synthesis reaction and others, taught us that to really understand the catalytic effect And to understand structure-function relationships in catalysis, you really need to know the energetics of the species involved and the transition states of all the elementary steps. The other thing that he taught us, and other pioneers like Salmerjai and Goodman and many others, is that if one wants to understand the structures of adsorbed intermediates, it becomes a task that in some cases is limited to single crystal surfaces, because it's really only on single crystal surfaces that you can cleanly produce individual adsorbed catalytic reaction intermediates. And so most of the structures that we know for adsorbed intermediates in catalysis are on single crystal surfaces, and they're also nice in that the state of the art in computational catalysis is density functional theory with periodic boundary conditions, and the periodic boundary conditions also implies single crystal surfaces. So it's a case where experiments on single crystals can be compared very directly to the calculations, state-of-the-art calculations. Erdl, already back before I worked for him in the late 70s, early 80s, had already been measuring the energetics of adsorbed intermediates, and essentially it's for species that adsorb reversibly. And so those could be studied by temperature-programmed adsorption, equilibrium adsorption isotherms, and those are known for many molecularly adsorbed species and a few dissociatively adsorbed species like hydrogen and oxygen that desorb again reversibly. Here's examples of temperature-programmed desorption measurements of the desorption activation energy, which is essentially equal to the adsorption energy for a series of N-alkanes on different single crystal surfaces. So that technology to do that for reversibly adsorbed species has been around for decades. But for molecular fragments, such as these, we didn't really have a handle on those adsorbed intermediates energies, simply because you can't adsorb and desorb these things reversibly and use those techniques. This list here is sort of the simplest examples of the kinds of functional groups on surfaces that are the ubiquitous intermediates in most of energy and environmental related catalysis. And until some of the measurements I'm going to talk to you about today, the energies of those things were not known experimentally for any surfaces. Dave King, now Sir Dave King, recognized this early on, and he built a calorimeter that could actually measure the heats of adsorption of things that were irreversibly adsorbed on surfaces. And it was the first time that that kind of measurement could be made on a single crystal surface. And we followed his techniques. I won't talk much about it, but we invented a new heat detector that's about 400 times more sensitive than his heat detection method. And at liquid nitrogen temperature, that's at 300 Kelvin. Liquid nitrogen temperature, it's about 10,000 times more sensitive, so you can do a lot of experiments that he wouldn't even be able to attempt with his heat detector. And so I'm going to talk for a little bit about the energetics that we measured. Here's an example of getting at the energetics of adsorbed hydroxyl groups. And I put this long list here of citations up to remind me to acknowledge the fact that the systems I'm going to talk about are systems that had been studied extensively already in the surface science literature on single crystals using surface spectroscopies, various structural characterization techniques. So we know what the structure is that we're producing. For example, it's known that if you have a platinum surface and you adsorb oxygen atoms first, and you dose water to that, you make this one-to-one hydroxyl water complex on the surface that has this structure that's shown here where the hydroxyl groups are hydrogen bonded to waters. And it doesn't matter if you start with a low oxygen coverage or the saturation amount of oxygen on the surface. As you dose water, you get essentially the same heat of formation. That's because you make islands of this structure locally, no matter where you start in oxygen coverage. I'm going to talk about coverage here in units of monolayers, and it's always going to be defined as the number of adsorbates per metal surface atom. And so once we have this heat, we can extract out of that heat of reaction, since we already know the heat of formation of this species from temperature-programmed adsorption, the heat of formation of this species. And since the waters are hydrogen bonded to the hydroxyls in a way that's very similar to the way water molecules hydrogen bond to themselves in a pure water add layer on platinum, If we assume these waters have about the same heat of formation, then we can extract out of that also the heat of formation of the hydroxyl species that are co-absorbed with the water in that structure. I put this up to show the flexibility that we have with the calorimeter. These are measurements of the heat of absorption of diiodomethane at different temperatures on platinum. And at very low temperature, when you absorb this molecule, the two iodine atoms cleave off and you make CH2 and two iodine atoms. Whereas if we go up to 210 Kelvin, two iodines and a hydrogen cleave off and we make a CH2 or CH group on the surface. And so this top curve here just blown up, and you can see extract from that the heat of reaction. Because we know the heat of formation of iodine atoms from temperature-programmed absorption and hydrogen atoms, we can get the heat of formation of the CH group on that surface. And so here's a collection of such measurements. We can get the heat of formation of methoxy groups from the analogous reaction to the water dissociation where we have oxygen. You lose the acid hydrogen, if you like, on the methanol to make methoxy and OH. If you similarly absorb formic acid, you lose the acid hydrogen to make formate and OH. And depending on the temperature where you do that experiment, you can either make monodentate or bidentate formate. You get a handle on both of those. Methyl iodide gives you methyls. T-butyl iodide gives you T-butyls, and so forth. And so we can get the heats of formation of these molecular fragments on surfaces in that way. So putting those together, we can start to make energy diagrams for important reactions like methane activation. So this is methane gas, weakly absorbs to make methane on the surface, loses one hydrogen, that's almost thermal neutral. It loses another hydrogen, that's way uphill, and then finally the third hydrogen, and it's way downhill again. So we can get a handle on the energetics of the overall steps. We teach freshman chemistry, and I teach my students, if you know the heats of formation of all the reactants and products for any reaction, you can calculate the overall delta H for that reaction. Here's two reactions in forward and reverse that we now know the heats of, the enthalpies of these reactions. You can see it's easier to make methoxy starting from oxygen than from hydroxyls on platinum. And those are reactions that would be essentially impossible to do in a vacuum chamber in the kinds of experiments that I talk about, so we couldn't get that reaction energy except for by combining the enthalpies of formation. And similarly, we can put together the energy diagram assuming no solvent effects for the important fuel cell reactions of formic acid and methanol oxidation, starting from methanol or formic acid gas to make CO2 and water. And when one puts together all of the energetics that we've measured for adsorbed intermediates or other people have measured for some of the simpler ones, we can really get the full, if you like, energy diagram for those mechanisms. This is, I think, by far the most complicated energy diagram that's been ever done in catalysis for experimental measurements. Of course, nowadays we see energy diagrams like this all the time that are done from density functional theory. And in fact, this reaction, or these two reactions, had been studied very widely with density functional theory for applications in understanding fuel cell catalysis on platinum electrodes. I should thank the students that are involved. Wanda Liu's whole dissertation was about how to get this calorimeter to work at a variety of temperatures. Junfa Xu, who's here in the audience somewhere now at USTC, was a postdoc in the group and helped in improving the detection capabilities for our calorimeters, as did Ola Lutkin, who came from Korkendorf's group, and Jonathan Harris, who came from Dave King's group. And Jason Farmer also contributed quite a lot. Michel Gottfried, who's a professor in Germany now, was a postdoc and contributed a lot. Izzy Green as well. And the data that I showed for formic acid, methanol, methane, and diiodomethane and so forth was all from these two chemical engineering PhD students' dissertations, and they deserve hats off for some really hard work that was shown there. So I started these experiments because I wanted to understand the energy diagrams for catalysis of hydrocarbon reactions on platinum. But in the course of doing these things, I've discovered that there's actually a much more important role in catalysis research that these measurements play, and that's as benchmarks for guiding the evolution of more accurate computational methods for predicting the energetics of catalytic reaction intermediates on surfaces. And in fact, I think the future of catalysis is going to be, a large part of that is going to be computational discovery of better catalytic materials and processes. And so I'm going to show how these energies are being used to make better density functional theory methods. And so here's a paper that I published together with Jens Norskov and his group. And I think my battery might be out on the pointer here. You have another one. But Jens is a computational leader in catalysis research, and he realized the importance of more accurate density functional theories. He's used smaller databases of experimental energetics of adsorbed species to try to make better versions of density functional theory, particularly RPBE. Thank you. and Beef van der Waals methods. And so this is a database that we put together. It's not the limit of everything we know, but it's 39 reactions that together we thought would be representative of adsorbates on late transition metals that could be used by physicists who are trying to develop better versions of density functional theory. And here are comparisons of those experimental results to the results from some of the most common versions of density functional theory, PW91, PBE, RPBE, and Jens's Beef van der Waals techniques. And we've sorted these errors out into two categories. These are for pure chemisorption systems, small molecules like CO, oxygen, small adsorbates, hydrogen atoms, NO. And these are the subset of that group of reactions, experimental reactions that have large contributions from van der Waals interactions. And the red errors are kind of not interesting. They're signed errors, so the negative errors cancel with the positive errors. Look at the other error bars that are in the other two levels here. They're pretty big errors, actually, in state-of-the-art density functional theory for adsorbed species. So it's especially when there's large contributions from van der Waals interactions. And these are the errors per adsorbed fragment. So if it's a dissociation reaction, you actually have to measure those or multiply those errors by 2 to get the real error for the dissociative adsorption reaction. When we published that, I was thinking that Angelos Michailidis' OpB86 van der Waals or OpB88 van der Waals methods might give better results for those kinds of molecules with large van der Waals contributions. And so together with Yi Zhu and John Sabine McEwen, who are young chemical engineering professors, we compared our experimental measurements table to the results from these. And in fact, they do quite a lot better for these, but they do much worse for the small adsorbates that are strong chemisorption species. But we put together a method to combine RPBE with these OpB techniques to get a new DFT-based approach for estimating adsorbate energies that's more accurate by far than the other techniques that are much more commonly used, and almost as accurate as beef for the smaller adsorbates, so that the overall errors are the smallest for this new methodology. This paper was just submitted to Angewandte Chemie. We also just submitted a paper that has a larger database, 81 adsorbates on 11 different metal surfaces with 26 different faces of transition metal surfaces. So that should appear soon for those of you that are interested in databases of accurate experimental adsorbate energies. All of the molecular fragments that I talked about so far were on platinum, and so we've moved recently to nickel. And so here's an example of methyl. The heat of formation of methyl on nickel can be extracted from these measurements of the dissociative adsorption of methyl iodide. There's very little known. There's really only two dissociative adsorption reactions whose energy is known on oxide, transition metal oxides. And here's one of those, dissociative adsorption of water on nickel oxide, and dissociative adsorption of water on iron. Fe3O4 is the other system. So there's a dramatic need for database on oxides. I've been working for about 3 years on oxides, and it's really hard to produce molecular fragments on oxide surfaces that have well-defined structure because there's so little surface science literature telling how to proceed to do that. I should thank Dr. Wei Zhao, who's a postdoc in the group, came from USTC, and Jianfa Shu's group, and Spencer Carey, who has discovered that he has to become one with the instrument to make these difficult measurements. So I'm going to talk next about making microkinetic models from these kinds of energetics and from the transition state energies to predict catalytic reaction rates and how to analyze those with some methods that we developed in the group. And here's an old example of a microkinetic model shown schematically here as the energy diagram for the water-gas shift reaction on a copper single crystal surface. And so these energy levels were all determined from experimental measurements, and we could put those together and we also measured pre-exponential factors for those, or obtained those from the literature. Could put those together into a computer to predict the reaction rates at different pressures and temperatures, and in fact found agreement with the experimental measurements of reaction rates is highlighted in this paper here. And so this is what I call a microkinetic model, where you have all the elementary steps, all the rate constants in the forward and reverse directions for all those elementary steps. Or perhaps a better way to say that is if you know the standard state free energies of all the minima and the maxima in this kind of an energy diagram for the reaction. It's much more common nowadays to see microkinetic models that are based on density functional theories, and here's an example from Manos Mavrakakis and Lars Grabo, who's in the audience somewhere, and Jim Dumesic, where they used density functional theory to study the same water-gas shift reaction, but on platinum 111. And these are the elementary steps. And this was an important paper because it first talked about this carboxylate intermediate that's crucial in that reaction, which reminds me to point out, I show the errors, and I'm sort of become famous for pointing out the errors in density functional theory, but I also am a strong proponent of density functional theory, and it really has helped us tremendously in the science of catalysis. And one area that's super critical is understanding what the mechanisms are and what are the key intermediates. It's very common that under steady state reaction conditions, a key intermediate has a coverage that's only 1/millionth of a monolayer. You just would never capture that really with any kind of experimental techniques. And so to know, for example, that this COOH intermediate, exists, one would really have to rely on something like density functional theory to show that. So we've discovered that in analyzing these kinds of microkinetic models, there's a concept that we invented called the degree of rate control for elementary step I that is a powerful tool, and it's the fractional change, or it's the change in the reaction rate per change in the rate constant for elementary step I, holding the rate constants for all the other elementary steps in the mechanism, and the equilibrium constant for that step constant. And it's normalized in this way so that it's really the fractional change in net reaction rate to the product of interest per fractional change in the rate constant for that elementary step. And it turns out if you have a simple mechanism where you can work out an analytical rate expression and it has a single rate determining step, then if you do this operation, you discover that the degree of rate control for that rate determining step is 1. And you also find for sequential reactions at least that the sum of the degrees of rate control for all the elementary steps is 1. So it's for simple analytical rate expressions, it's common to have the degree of rate control 0 for all the elementary steps except for 1, and the rate determining step has a degree of rate control of 1. And it's best to picture the meaning of that concept when you look at it on a standard state free energy diagram for the overall reaction, where there are many elementary steps. And so this degree of rate control, if you expand the rate constant in terms of the standard state Gibbs free energy of the transition state for that elementary step, it really tells you what's the fractional increase in the reaction rate per unit stabilization of the transition state for that elementary step. And that's 1, that number is 1 for the rate determining step. When you look at it this way, you realize that you can do the same operation also for all the minima in the standard state free energy diagram for the reaction. And so it's how much the rate increases fractionally per unit stabilization of the adsorbed intermediates. And those things tend to be negative numbers because when you stabilize adsorbed intermediates, it actually poisons the net reaction rate. So here's an example of a solved microkinetic model for the methane steam reforming reaction at these conditions using energetics from density functional theory for rhodium-211 in collaboration with theorists from Jens Norskov's organization. And these are the degrees of rate control, and these are for the transition states, that is for the elementary steps that have these transition states. And you can see that the degree of rate control is essentially 0 for all of the elementary steps except 2. And this is almost the rate determining step, but this has a substantial degree of rate control. And for the adsorbed intermediates, the degree of rate control is essentially 0 for everything except for these 2 adsorbed intermediates that have negative degrees of rate control. That is, if you stabilize those species, then you slow the reaction rate down. And so all these zeros mean that if you change the energy of that species, it doesn't affect the reaction rate at all, at least for small changes in the energies of those species. And so it teaches you how to think about many things, aspects of the kinetics of reactions and how to study those. I just heard Jeff Greeley speak a couple of weeks ago at the Gordon Conference in catalysis, and he showed that he uses his degrees of rate control in his microkinetic models based on density functional theory to discover which species energies are sensitively controlling the rate, and then he goes to a higher level, more costly version of density functional theory to get better, more accurate estimates of those energetics. So that's a wise use of that. And so it's also very powerful in analyzing how to improve the reaction conditions if you have a microkinetic model for a reaction. I'm going to show an example for a model, density functional theory model of MOF encapsulated palladium and palladium silver nanoparticles. And so it's kind of like a nanoparticle or a cluster in a zeolite. When the reactant comes along, it has to line up along the pores of the metal organic framework. And so, for example, in this case, for butane, the palladium can only be accessed from the end carbon atom of the butane molecule. So it causes regioselective oxidation. Here's a cartoon of the surface that we studied together with Rachel Getman's group for this. It's a silver palladium alloy trying to make 1-butanol out of butane. And what we did is we looked at the degrees of rate control, and the original plan was to try to find better catalytic materials using something I'll talk about next. But what we discovered is when we looked at the degrees of rate control, there were obvious ways to greatly improve the catalyst by just changing the reaction conditions. And so here's 3 different sets of reaction conditions. This was the conditions that they started out with in Rachel Getman's group. It was basically with consuming the small amount of butanol that was there. We finally got a healthy turnover frequency for butanol and a high selectivity for the 1-butanol that we were interested in. I won't go through the details. It's a little gory about how to do that, but it turned out that once we made those changes, the net reaction wasn't oxygen plus butane going to butanol, but we added water to the feed to get more hydroxyls on the surface, and the net reaction was this, where 3 out of 7 of the oxygens in the product were coming from water. And that really led to tremendous selectivity. It gives ideas for how to do selective oxidation, I think, in catalysis. So I mentioned earlier that computational discovery of new catalytic materials, I think, is going to be very, very important in the next era in catalysis research. Jens Norskov has been sort of the strongest pioneer in that area, and his group, especially Thomas Bligard and Frank Abel Peterson. And here's an example of one of their volcano plots for discovering new catalyst materials based on this descriptor approach, two-descriptor approach that he developed. And I'm sure many of you are familiar with that type of approach. We've recently described a new way for doing such computational searches for better catalysts based on density functional theory that don't require the linear scaling relations, which is an approximation in his approach. And without belaboring the math, we take the definition of the degree of rate control, we integrate that, and we can then computationally predict the rate of the reaction on a new material relative to the rate on a reference material based on only the DFT energy differences between the energy of the species involved in the mechanism on the new material relative to that on the reference material, and the degrees of rate control for those species on the reference material, summed over all species in the reaction, transition states, and intermediates. That looks like a mess, but remember, this thing is zero for almost everything in the reaction, and so you're only actually summing over a few species here, so you only need a few energies here for the new material to predict the reaction rate for that new material. You can also predict selectivities in sort of a similar way. So here, this is that same reaction I was talking about before, methane steam reforming. We took rhodium-211 as a reference material, and all these guys, energies don't matter. You only have to calculate the energies of those guys on the new materials to predict the reaction rate. And the assumption is that the degree of rate control is the same on the new materials as it is on the reference material for which you calculated the degrees of rate control. And so this is a plot to try to show how the degrees of rate control depend on the nature of the material. And so I've resorted to Jens Norskov's descriptor space for this reaction, the binding energy to oxygen and carbon for the materials. And here's our reference material. And these colors, these are for intermediates and these are for transition states. The colors refer to when that species has a high, almost unit degree of rate control or a -1 degree of rate control. For example, in this region, breaking the carbon-oxygen bond is the rate determining step. In this region, breaking the carbon-oxygen bond is here. Breaking the CCH3 bond is in this region here. And over here, adsorbed oxygen is rate controlling as an intermediate. In this region, carbon and CO are rate controlling, and here carbon and oxygen are rate controlling adsorbed intermediates. If you look at that, you realize that there are huge regions in descriptor space or in material space where the degrees of rate control are staying constant. And so our method is accurate in regions where they stay constant. But we found that we got as good an agreement, if slightly better, than Norskov's method, even in this region, for species limited to relatively close, within 0.5 eV in descriptor space of the reference material. So I think particularly when you're looking at new processes, totally new classes of materials, it's a great way to go forward to try to find ideas for better catalyst materials. This just to emphasize that it's actually computationally cheaper than the Norskov method, as long as you're looking at less than 100 new materials. That's simply because you don't pay the cost for developing all of the linear scaling relations in our approach. Chris Walcott was a PhD student who did that to go with Felix Stute and A.J. Medford at SunCat in Jens Norskov's organization. I put this here to acknowledge that Jim Numesic has been a real pioneer in In fact, has used more than I have the degree of rate control for transition states in analyzing microkinetic models. He just published a paper in PNAS a few weeks ago where he used the degree of rate control together with his maximum rate analysis method to actually calculate the reaction rates in microkinetic models without having to solve all of the differential equations that you have to solve to calculate reaction rates from all of the elementary step rate constants. And it's a great paper. I encourage you, if you're interested in these kinds of things, to look at it. But I also put it up here because everything I've talked about has been associated with gas phase catalysis and the energetics of those reactions. But one of the things he's teaching us with some beautiful experimental examples recently is the importance of solvents and all of these energies, and the fact that that's a very important new direction for catalysis research. These systems where there are large contributions from van der Waals interactions are certainly going to become more important when we look at catalysis at the liquid-solid interface, and so DFT-based methods that can accurately calculate systems where the large van der Waals contributions are highly important. So I encourage the community to encourage funding for people that are developing new methods like that. I'll just use that slide because I happen to have it with a picture of Jim on it. So next I'd like to talk about the metal energetics, that is the energetics of the metal atoms in these particles. And of course, a real catalyst has metal nanoparticles supported on oxide or carbon type of a support. And we've heard a lot of talks already in this conference. There are particle size effects when you're below about 6 nanometers, particularly in particle size. And there are important support effects that particularly manifest themselves when the particles are in that small size regime. Maintaining active catalysts for long periods of time is important, particularly if you have sintering taking place at the reaction conditions of interest. And I'm going to talk about the energies of these metal atoms and how they impact these types of things. And a key concept there is going to be the concept of the metal atom's chemical potential, which depends on the particle size and the support material upon which the particle sits. And to show that, we resorted to model catalyst again based on single crystal surfaces, in this case single crystal oxides, as models of the support material, and metal nanoparticles that are grown on those by vapor deposition of gas phase metal atoms. And so here's an example of the type of model catalyst that I'm going to be talking about that has silver nanoparticles on cerium oxide. And this is from nice, beautiful STM images from USTC and Junfa Shu's group. And you can see that the particles decorate the step edges on the ceria. And a few important points about the way these particles grow. When you evaporate a metal onto an oxide, they go through a nucleation stage in the first about 1% of a monolayer, and they grow clusters. And after those clusters form, as you go up in coverage after that, the number of clusters doesn't change. The individual particles just grow in size, and that's because metal atoms land on the surface and they migrate around and they find an existing cluster to add to. So we can control the average particle size by just controlling the amount of metal that we've added to the surface after about the first 1% of a monolayer. And so we're doing experiments where we now, instead of having a molecular beam of a molecule to do the calorimetry, we have a molecular beam of metal atoms, and we grow nanoparticles and grow those bigger. And so that allows us to measure the heat of adsorption, in this case of copper atoms onto ceria, that's slightly reduced ceria, as a function of the average particle diameter to which that metal atom adds. So it's the difference in energy between gas phase copper atom and a copper atom in the nanoparticle at the particular particle size that's the average particle size at that coverage. And so these are two experiments, one at room temperature and one at 100 Kelvin, where the copper atoms are much less mobile on the surface. And at 100 Kelvin, We can actually get copper monomers. The first 2 data points are for copper monomers on terraces because they're so immobile, and then you start nucleating particles and they grow bigger. At room temperature, you already make a dimer in the first pulse of gas, and as the step edges are titrated, the heat of absorption decreases, and then it grows again. And this growth, the overall growth, is a very common result, that the heat of absorption increases with particle size, and it can be understood very simply from the number of metal-metal bonds that are made. If you imagine that you have a dimer and you absorb another metal atom to that, the most metal-metal bonds you can make are 2 to that new metal atom, plus it has a bond downward to the oxide below. When you have a trimer, you can make 3 bonds. By the time you get to a large particle, on average, you make 6 metal-metal bonds when you add a metal atom to a particle in the large size limit. So this is basically like making 6 metal-metal bonds. You can see it drops down by a huge amount, largely because you're making fewer metal-metal bonds in the absorption energy. We can take these type of data and extract out of that, basically flipping this axis upside down and re-zeroing. We can extract out of that the change in the chemical potential of the metal atoms in those particles as a function of the particle size. And the chemical potential starts very high for small particles, and it decreases, eventually leveling off at 0 on this plot, which is the chemical potential of a metal atom in the bulk, infinite large particle of the metal. And this decrease is the thermodynamic driving force for sintering. This is why it's hard to keep metal atoms in small clusters, because they're less stable by, for example, on MgO, they're less stable by 80 kilojoules per mole of metal atoms than a large particle of MgO that's bigger than 6 nanometers. The other thing you can see from this is that the metal atoms on MgO are much less stable for the same particle size than if they're supported on a slightly reduced Syria, and more reduced Syria is even more stable. And this difference really has to do with that other bond. Okay, this decrease has to do with the fact you're getting fewer metal-metal bonds as you go to smaller particles. But the difference for the same particle size here is associated with the fact that there's also bonds of the metal cluster downward to the oxide. And the stronger that is, the further downhill you are in chemical potential. The more I've worked with this type of data, the more I realize how clever Gibbs was with the name chemical potential. It really describes the potential with which a species, the potential of the species has to do chemistry. And the higher in chemical potential, the more aggressive the species is. And it's really going up this hill is like tuning to the left in the periodic table. And really, I think this is one of the reasons why small nanoparticles of gold can do catalysis that's more like something a little bit left in the periodic table. It's no longer as inert because it's the metal atoms in small particles have high chemical potential. They're more aggressive at their chemistry. And I'm not going to talk about the results of that today, but there's many examples where we and others have found that the absorption energies of small species like oxygen and CO are stronger, as evidenced from temperature-programmed absorption, on smaller particles than they are on larger particles. But there's a secondary effect, and that is that the chemical potential decreases the more strongly the cluster binds to the oxide support. So you can also tune the chemical reactivity for the same cluster size by tuning the nature of the support material upon which it's attached. And again, this decrease is related to the driving force for sintering. And so it turns out that if you think about the way a catalyst sinters, you have metal clusters. Sintering is when you get fewer metal clusters and they get bigger. And the way that happens usually is by Ostwald ripening, which is that metal monomers leave one particle, diffuse across the surface in a random walk. If they bump into and attach to a bigger particle, they're lower in energy, and therefore they stay there. And the rate of sintering is really controlled by the concentration of these diffusing monomers that give rise to the Ostwald ripening. As you go downhill in one of these systems, you're decreasing the chemical potential of the metal atoms in the nanoparticle by huge amounts. And the equilibrium concentration of these diffusing monomers goes down by E to that amount over KT, over RT. And so this is 80 kilojoules per mole. So the concentration of diffusing monomers here compared to the large particle is E to the 80 kilojoules per mole over RT of your catalyst operation. That's a huge number, many orders of magnitude. And so the sintering rate's high here, but by the time you get down to here, the monomer concentrations just dropped down and the sintering rate goes way down. And so this explains a lot about the details of how sintering rates depend on particle size. So let me just go through some recent results of these measurements of the heats of absorption of metal atoms. In this case, we're measuring the heat of absorption of gold on ceria, slightly reduced ceria, at two different temperatures, 100 Kelvin and 300 Kelvin. And again, the first data point here is at the size that is 1.1 atoms. So it's essentially monomers on terrace sites at 100 Kelvin. And the particles grow on terrace sites at 100 Kelvin. At 300 Kelvin, the particles diffuse to step edges where they're more stable and they have a slightly higher heat. We think that there's data points that could be had here, but the gold monomers diffuse tremendously rapidly, and by the time that you get your first point of measurement here, it's already grown a cluster that's about 8.8 nanometers in diameter. So we couldn't experimentally access that smaller clusters at step edges. So go back and show you we could get dimers at step edges for copper. Copper is less mobile than gold monomers on the same surface there. Gold absorption on magnesium oxide is quite different. In most of these systems, the particles grow with something that's approximately hemispherical shape, and you can sort of see that in that SDM image from Jim Flashu's group. But for gold on MgO, it's a strange growth. It makes bilayer islands to start with. And so that's islands that are 2 atoms of gold thick. And the islands grow in lateral dimension as you add more and more gold to that without getting thicker until they get to about 7 nanometers in diameter. And then the islands stop growing out at all, and they grow straight up after that. It's a strange growth mode. You can understand it from the kinetics of the process, but that's what happens. And so there's 2 regimes. In this regime, we can plot the heat of absorption essentially as a function of the average 2-dimensional island size for islands that are always 2 atoms thick. You can see there's quite a difference between 100 and 300 Kelvin because these are at step edges and these are on terrace sites. So that emphasizes the difference between clusters on defects and not on defects. In this size regime, basically the islands are 7 nanometers in diameter and they're just getting thicker, and you see an effect as well there. So these energetics of metal binding, I think, are crucial to knowing how to go forward in choosing support materials to do what you want to do in catalysis. And crucial to that is knowing how the different support materials control the chemical potential of metal atoms in particles of the same size. Like here, it's clear that silver atoms in 2 nanometer particles are much higher in chemical potential than on these more reducible oxide surfaces by like 60 kilojoules per mole or so. And why is that is the big question. And can we understand the systematics of how one oxide controls to have low chemical potential and another oxide has metal atoms that have high chemical potential for the same particle? And Really, it has to do with the adhesion energy at the interface between the metal nanoparticle, our cluster, and the oxide support. And so we've been extracting from our calorimetric measurements the adhesion energy. Adhesion energy is, by definition, the energy it takes to separate the cluster off of the oxide support, if you like. And so these data in black points here for magnesium oxide have already been published in 2013. And they come from not just our calorimetric measurements, but also from analysis of the particle shape using electron microscopy or X-ray scattering measurements. And those all seem to fit on the same trend here for magnesium oxide, where this is an axis that has something to do with the nature of the metal that's supported on MgO. And this axis is the heat of sublimation of that metal in the bulk, and the heat of formation of the most stable oxide of that metal per mole of metal atoms. And basically, this is the energy difference between a gas phase metal atom plus O2 gas and a metal atom in the most stable oxide of that metal. And that means it has something to do with the strength of the metal-oxygen bond. And that this adhesion energy should correlate with that. Strength makes sense because when folks do density functional theory of metals like these on oxides like these, they find that the metal atoms prefer to sit on top of the oxygens. That is, they're bonded primarily to the oxygen atom. So the strength of metal-oxygen bonding should correlate with the adhesion energy, as we see here. It does. These are new results for slightly reduced Syria. And these things are following sort of a similar slope, but much increased. In fact, you can see that the extra adhesion energy from going from MgO to Syria is bigger than the whole range of effective metal on the adhesion energy. So it's a huge effect. The support plays a huge effect. Since these things have sort of quasi-parallel slopes, we are sticking our necks out here, and based on single individual measurements on other oxides, we're drawing sort of a semi-parallel line here to that. Iron oxide, Fe3O4, alumina, TiO2. So it gives, I think, the first sense experimentally of what these, how adhesion energy depends on the nature of the oxide and the nature of the support. I should point out that in this review article, we show that the adhesion energies that are measured and are reported here are in the clean conditions of ultra-high vacuum, where the surface of the oxide was verified to be clean. And those adhesion energies are 2 to 3 times larger than the adhesion energies that have been measured by other techniques that are not in ultra-high vacuum. For example, the contact angle measurements in hydrogen gas for molten metal particles on oxides that are kind of old measurements. Consistent with this trend, gold monomers bind slightly more weakly than copper to Syria. If you look here, gold's here, copper's there. Gold binds more weakly than copper. In fact, for monomers, this is for basically in the large particle limit for the adhesion energy. But for monomers too, you see similar qualitative trend as well. Those 2 points are as far as I know, the best experimental benchmarks of adsorption energies, the only experimental benchmarks of adsorption energies of metals on oxides of the type that are interesting in catalysis, and so they should be used to see whether density functional theory is doing well at those kinds of approximations. I will say that when we started making these measurements for gold, silver, and copper on Syria, I was amazed because silver and gold both clearly preferred to bind to oxygen vacancies on Syria. We tested that by making more oxygen vacancies on the surface and measuring the difference in the heat of adsorption of those metal atoms on those. But for copper, it did just the opposite. Copper doesn't like oxygen vacancies, and I thought, why is this? The real reason is because copper is more oxyphilic, and it just doesn't like oxygen vacancies, whereas silver and gold don't like oxygen that much, and the vacancy defect is a nice place. But that was already in the literature before we made those measurements. That is the density functional theory result. So at least that level of prediction is accurate in density functional theory. These kinds of measurements led us to have some ideas for how to make better sinter-resistant catalysts. And we had a collaboration with Yunan Shah's group, who's at Georgia Tech now, but started out as a professor in our department. And so he and I have collaborated over the years. And one of the ideas that we had that we were funded by Toyota to pursue was to make a, if you like, nanostructured support material that had two kinds of oxide supports, weak oxide support, completely surrounding small nano domains of a strong oxide support. By weak and strong, I mean an oxide that binds the metals weakly and one that binds the metals strongly. And if you think through the kinetics of sintering on such a surface, if you can make a catalyst where you only have one metal cluster per domain of strong oxide, the rate of sintering should be slower. In fact, that turns out to be the case. Wayne Goodman first showed that by depositing titania on a silica surface in the presence of oxygen, and it grew titanium. It grew TiO2 islands on silica, and then he evaporated gold onto that and looked at the sintering of that with scanning tunneling microscopy and found that that kind of a structure sintered much more slowly than either gold on TiO2 alone or gold on silica alone. And so we made some similar things from wet chemical synthesis techniques. Really, Yunan Shah knows how to do that beautifully well. And here's an example of a material that he found out how to make that's like that. It has platinum nanoparticles that are bonded to TiO2 but completely surrounded by SiO2. You can see that here is a platinum nanoparticle that has TiO2 support that is bonded to, but it's surrounded by a few layers of silica, and that sinters more slowly than the TiO2 or the platinum on the TiO2 or the silica separately. And this had been done previously by Peter Stair's group and the group at Argonne National Labs that do atomic layer deposition, and they had grown this silica by using atomic layer deposition. We think this is a better method because you can use wet chemical techniques. I should say we happened, because we had platinum nanoparticles, we grew the platinum nanoparticles using fancy Yunan Shah type synthesis, but that's not really necessary for the second step, which is adding the silica around that. So I think it's a technique that could be used for real catalyst synthesis. I should thank a few people here. All these characters over here are the graduate students that are responsible for the recent results of metal absorption energies in our group, particularly Trevor James, who just got his PhD about 6 months ago, and Stephanie Hemmingson, who's going to get her PhD this summer, and James Sharp, who pioneered some of these measurements on the Syria with Jason Farmer, whose picture I showed earlier, who was one of the guys that was instrumental in making our calorimeter sing better, and Gabe Feely, who's the newest student on that project. They're really working hard. And Jason Sellers, whose dissertation was all about how to make a calorimeter that could measure the absorption energies of things with low vapor pressures like gold, and now we're working on platinum, that can make a well-defined molecular beam of platinum atoms or gold atoms. That's the hardest part of those measurements, I should say. The whole group has to work together. These are hard experiments, and so my hat is off to all of them, particularly for their teamwork. And I have to say they did a great job on that. There's a whole ton of other people. Todd Stuckless, who came from Dave King's group, helped construct the first calorimeter in our group. And there's a whole ton of people from the group over the years that have helped in various ways with the things I talked about. Jens Norskov has really been an inspiration in pointing to me how important these energies are to going forward, I think, in the long-term picture of at least basic research in catalysis, if not in practical research led by computational catalysts discovery. We should thank the funding agencies. National Science Foundation funded us for our first construction of a calorimeter, and they still funded our work on these molecular fragments that I talked about on platinum and nickel. The Department of Energy has funded everything else that I talked about essentially, particularly the attempts we're making to get at molecular fragments on oxide surfaces, a very difficult challenge. All the metal absorption energetics, all the work I talked about on the degree of rate control in the kinetic modeling and so forth, and a grant from DOE through SLAC with Jens Norskov as a PI, and a grant from DOE through the University of Minnesota on their ICDC. We heard something about the ICDC research from Bruce Gates earlier this week when he was talking about the clusters in the MOF results, beautiful results there. So I think that's all I have to say, except for I really want to thank you for your attention and for inviting me to come here. It's wonderful to have this opportunity.